Okay, so today we're going to be going over AVL trees. Prerequisites is knowing what linked lists and binary search trees are. Here's an example of a binary search tree on the right, just pretty basic, smaller nodes on the left or larger nodes on the right in terms of what data value they're holding. What AVL trees are essentially binary search trees that self-balance themselves after inserting or deleting a node. It's used to avoid the worst case scenario for binary search trees when either the left or right side is either too long or too short, and that causes inaccurate or inconsistent search times. And that's pretty bad when managing data in the programming world. There's a similar type of self-balancing binary search tree called red and black trees. So it would be obvious to compare this to that. Compared to a red-black tree, AVL trees have faster lookup times and are used primarily for databases. If you're familiar at all with red and black trees, you'll know that it's also just better for insertion and deletion. If you want to look up why it's better, feel free to do so. AVL trees are also balanced when the difference in the heights between the left and right subtree is not greater than 1. And so that's when they're balanced. So the left and right subtree of each node has to have a difference not greater than 1. That'll be explained better in the examples. But for now, just take that at face value. And keep in mind that it does apply to all nodes in the tree. And AVL trees are unbalanced when that difference in height is greater than 1. And that's when you make a change to balance that tree out. And an interesting bit of trivia is that the max height of an AVL tree is always big O log n, or log n using big O notation. Alright, so here are some examples. On the left we have a balanced AVL tree. So a bunch of nodes were added, and so far it's now a balanced node. Let's say, for example, that 4 was a newly node that was just added. In order to find out whether this tree is balanced or not, you start counting at that newly node, so that node makes 1, and then we essentially, you start out by counting the nodes left and right subtrees, but since 4 was just added, it has null and null for its left and right subtree, making a height of 0 and 0, which difference is less than 1, so you don't have to worry about that. And then we technically move up to 5, and we know that because we came from 4 that it's only one node, so the height is just 1, and its right subtree is null, so it's got a height of 0. Difference between the two is 1, which is not greater than 1, so far both of these nodes are balanced. And then we take the largest height of the largest subtree, or of either subtree that we found, and then add 1 to it, so that's how 5 becomes 2. And then we're essentially at 8, so we know that the left subtree height of 8 is 2, and then we try to find the right subtree height. And here there's only one node, so we start at 1. And then we say the difference between the left height and the right height, which is the difference between 2 and 1, is just 1, so we know that 1 is not greater than 1, so 8 is still balanced. Then we go to 12, and that means that this becomes 3 because we add 1 to the largest height. And then we need to find the height of the right subtree of 12. So we go to 18 and then 17, because 17 is the end of that subtree, or the end of the longest chain of that subtree. And then you start counting. So 1, and then we have 0 for the right, so difference between 1 and 0 is 1. So then that tree from 18 down is balanced. So then 18 becomes 2, then we compare 3 to 2, difference is still 1, so from 12 down it's balanced, which means this whole tree is completely balanced. And now we look at an unbalanced tree, for example. So we'll say they added a node 7, and that didn't unbalance the tree. If you wanted, you could count, but we'll just kind of take that at face value for the time being. And then let's say they added 2 after that. So now the tree becomes unbalanced, and in order to find that out, we start counting. So obviously left and right subtrees of 2 are 0, And then you start counting at 4. You got 1 on the left for just 2, 0 on the right. Difference between 1 and 0 is 1, so there's no issue. 4 becomes 2. 7 becomes 1. Difference between 2 and 1 is 1. So 5's good. 5 becomes 3. We look at the right of 8. We just have 1 here. And then the difference between 3 and 1 is 2. So now we have a conflict at node 8, whose left subtree is larger than his right subtree, or the height of his left subtree is larger than the height of his right subtree. As such, we now have to do a course correct to rebalance this tree. Which brings us to our next slide, which is insertion and what to do when that causes an issue or whatever. So treat the node that you just inserted as W. So back here, 2 would be considered W. And then, whoops, I went back one. Okay, and then if, in this sense, when 7 was added, you would treat 7 as W, but since it didn't unbalance the tree, you were done there. But if the tree does become unbalanced, then you move up from W and you find the unbalanced node, which we did, and then you call that Z. So in this situation, 8 would become Z. And then you move back towards W, and then you call the next 2 nodes Y and X. So the kids of Z become Y and X. So we go back towards W, which is not 7 here, we just added 2. So 2 is our current W. We treat 5 as Y, and we treat 4 as X. And then in here, those 2 or 3 nodes can be considered or are arranged in 4 possible configurations. And we're going to have a look at those configurations now. So here, this is the left-left case. This is where Z, Y, and X are kind of in a line down on the left, which is the case that we were looking at here. Z, Y, and X are in that line. And in this case, you want to rotate right at Z. So at Z, you would rotate right. So Z comes down and Y goes up. The important key distinction to note here is T3. T3 becomes the left subtree of Z and is no longer the right subtree of Y. Or technically it's in the right subtree of Y, but Y's direct right node becomes Z. But do that and you're pretty much done. You keep, at that point you would move, once you reorganize this, you would move back up and check 12 and then see if it violates the tree in any way. And then the other case is a left-right case. So in this situation, Z, you move left from Z, and then in order to continue following the node that you inserted, which say could have been T2 or T3, you would have had to gone down to the right. So in this sense, because you went left and then right, the case is called a left-right case. And what you would do, you would start by rotating left at Y. So Y, you rotate left, and as such, X moves up and replaces Y. And here, the key thing to take away is that T2, which is a little tough to see right now, so I'm going to erase that. T2 is now the right subtree of Y, and is no longer the left subtree of X. And then if you pay attention, you'll notice that this is another left-left case, only this time, instead of Y, we have X. However, you treat it the exact same way. You would rotate right at Z, and then Z comes down, and X went up. And then, just like before, keep an eye on where T3 is, as it becomes the left subtree of Z, instead of the right subtree of X. And then we move on to the other cases, which is the exact same, just flipped. So we have a right-right case and a right-left instead of left-left and left-right. It's the exact same, just looking on the right side. Get a right line, so you would rotate left at Z instead of right before. This is when Z comes down and Y goes up. And as always, keep an eye on T2. It is now the right subtree of Z. For the right-left case, this is when moving back towards the node you inserted, wherever it is in T2 or T3, you went right and then you went left. And so X became the left node of Y instead of the right. And as such, you rotate at Y again, this time towards the right because that's the opposite side, of course. And so Y comes down and X went up. And once again, keep an eye on T3 as it now becomes the left subtree of Y. And then since this is another right-right case, you would left rotate at Z. So Z rotates left, moves down, and X moves up. And since X moves up, you once again need to take T2 into consideration, as it now becomes the right subtree of Z. And X's left node is now Z as well. Alright, moving on. Deletion, which is pretty much very simple. The node to be deleted is W. Delete it as you would in a regular binary search tree, and then if the tree stays balanced, then you're done, as with insertion. However, if the tree becomes unbalanced, you start again at W, which is where the node was to be deleted but is no longer there, and then go up, find the node that is unbalanced, and consider that node Z, and just do what you did for the previous 4 cases, and you will be able to balance the tree again. This will be better explained in the next few examples. Alright, so I've pulled up an AVL tree visualizer online. You can quickly Google one, and this one will pretty much be the first result, but it visualizes things quite nicely. So what we're going to do is just showcase how this works real quick. We're going to add 3 nodes randomly. We'll say 50, 30, so this will go on the left, yep. And then we'll do 70 for a node on the right. So now this is a basic binary search tree, and so far we haven't had the need to make any AVL tree balancing acts. You will, however, notice that every time it added the node, it counted them, so it was comparing them to its subtrees, essentially. So now let's try and recreate the 4 states that we went over, which was left-left, left-right, right-right, and right-left. Let's start with left-left. So in order to make a left-left scenario here, let's just keep adding a bunch of nodes on the left. So next we can add maybe 20. So it's going to go through. It's going to first find where to add 20 in a binary search tree. It does. Let's actually pause it here. Take a step back. So it added 20, and it started counting the nodes. And it added a 1 there. So then it looked to the next node. It's now comparing the left subtree to the right. 1 compared to 0 is 1. So therefore that node is good, and it's going to add the number 2 to it as such. Then it goes to 50. Compares left subtree to right subtree, 2 compared to 1. Our difference between 2 and 1 is still 1. And as such, that node is good. Add 3 to it. However, it's not comparing any numbers up top, so it's done there. And the tree is still balanced as a result. So we're going to add 10, which should add a node to the left of 20 and cause an unbalanced tree to appear. So we're going to insert that. It's going to go left again because it's a binary search tree. Oh look, there's an empty node. It's going to add it there. Start counting. 1 compared to 0 was 1. Then they looked at 20, they added 2. Now they're going to look at 30. 2 compared to 0 is 2. So we have an issue at 30, which is where it's going to realize, I think, yep. So it realized that there's an issue at 30. So it's in a left-left case, you rotate at Z, which is what 30 is currently. And Z gets rotated down. There's no right subtree attached to 20, but if there was one, that would be attached to the left of z here. And then it goes up to 50. 2 compared to 1 is still 1, or the difference between 2 and 1 is still 1. And as such, 50 is good. And so that was a left-left case. Now let's do a left-right case. So in here we could probably just add a node to the right of 30, which 35 would be good. We do a step forward, add 35 to the right. There we go. And then it starts counting up. 1 compared to 0 is 1, or difference between 1 and 0 is 1. Add 2 to it, go up. Difference between 2 and 1 is still 1. So that's good. Add 3 to it, and then go up. Difference between 3 and 1 is 2. So we have an issue at node 50. In this case, it's going to go back down. We're going to find that z is 20. Or no, sorry, z is 50. Y becomes 20. And then moving back down here, we'll find that x becomes 30. As a result, what's going to happen is this is a left-right case, so y is going to move to the left, x is going to move up, and if x had a left subtree here, it would become the right subtree of y, which happens. And as before mentioned in the previous slides, the right subtree of x becomes z in this situation. Which actually, you know what happened is it added the next step. So after that node, after y moves down and x goes up, it did the rotation at z, which comes after that. So z would move down to the right. And if x had any right subtrees, which it actually does, that right subtree becomes the left subtree of z. So it looks a little confusing because it does both steps almost simultaneously, but that's just the way computer visualizers are. So just keep that in mind when using this visualizer to test out your cases. But then you're done and the tree is balanced. So that was a left-right sub case, so now we'll do a right-right sub case. So we're going to add, let's say 80, so we can get it to the right of 70. We're going to keep going. And alright, so we compare 1 to 0. Difference is 1. Add 2 to that, then look at 50, compare 2 to 1. Difference is 1, so that's fine. Add 3, or change it to 3. Compare 3 to 2. Difference is 1, so that's fine. And then you change that to 4, but there's no need to anyway. So the tree is still balanced. Next up, we're going to add 90 to make it go to the right of 80. So we're going to keep going, and we add it. Alright, 1 compared to 0 is still 1. Change that to 2. 2 compared to 0 is 2. So we have an offending node at 70. Here we have a right-right case. So it's going to realize that. It's going to rotate 70 towards the left. And 80 is going to go up. Or I should explain it how the slide did. We treat 70 as z, and then 80 as y, and this time the node that was entered, which was w, is also considered as x. So it's going to rotate at z, and then becomes that simple. And don't forget, if y had a left subtree here, it would become the right subtree of 70. So if, for example, to showcase how that subtree would work, if we skip back to before I added 90, and instead if we added, we'll say 75. So this will go on the left of 80 here. We're going to add it, this might still cause an issue, I believe. Yeah, so we compare 1 to 0, still 1, 2 to 0 is still 2, so there is still a height difference. So we actually will just look at a right-left case instead of if that other one would have had a subtree. So in this case, because z, no, in this case we have z is 70, y is 80, and x is 75. So as with the other case, x is going to rotate right, and y is going to rotate right, and then x is going to move up, and then it's going to rotate z, which is 70, towards the left, so that x moves up as again. And then just keep in mind about the subtrees. In this situation, the left subtree of y would become the right subtree of x, and then once it moved up, its left subtree would have become the right subtree of z, which is 70. And it's going to continue to move up the chain of command here. It's going to compare 2 to 1, that's 1. Change that to 3, which is already 3. Compare 3 to 2, that's still 1. So the tree has become balanced. And that's all 4 cases described. And essentially, if you want to mess around with this, add more and more nodes, you can. But for now, we're going to move on to deletion, or just to showcase it. So for example, let's delete node. We'll delete node 35. So once we delete 35, you'll find that 2 compared to 0 is a difference of 2. And so it's going to want to rebalance the tree after that. So let's do that. Let's go down, find 35, delete it. Alright, so then it's going to look at 50. It's going to compare the left subtree of 50, which is 0 now, to the right subtree height, which is 2. And it realized that, so it is going to consider, since this was the offending node, we're going to treat this as z. Now normally you would have moved towards w, but because w was the node immediately preceding that, you would just consider w to be on either the left or the right subtree here. It looks like it is going to consider that to be on the, it's going to consider 80 to be x, essentially. Yeah. Alright, so in here it treated it as it was a right case, considering it considered 50 as z, 75 as y, and 80 as x. So as such, it rotated z to the left, and then y moved up. And this is one of those cases where, if you take a look, y's had a left subtree of just 70, so that became the right subtree of 50 here. And then the tree was then balanced and moved up, compared 3 to 2 again. Well, difference is only 1, so that worked out. And that's a pretty good example of deletion. And then you can play around further with that and see how far that takes you. But that's AVL Trees in a nutshell. So, hope you enjoyed.